Our main topic today is the logistic model of population growth. It's going to take the exponential model of population growth and make it a bit more realistic. Populations cannot grow exponentially at the same rate forever. There's limits on growth. There's the physical limit, say with people, that we only have so much land in the world. Of course, we could send people into outer space and they could try to live out there, but I'm not so sure of their success in living out in outer space or on Mars. Elon Musk wants to go to Mars, but I don't know. It's going to be hard for people to live on Mars, much harder than you might imagine. Radiation, lack of air, food, yeah, storms, dust storms. Okay, anyway, for the most part, there's limits on growth. We want to take that into account. We're going to let P be the population. Let's go ahead and say of robins in a certain area, maybe a forest. Later today, we're going to talk about robins eating worms, but not now. That'll be when we have interacting species, a predator, the robins, and the prey, the worms. But for the moment, we only have the predators growing. If the population is small at first, you would hope it would probably grow exponentially, or you would think it would. But once the population of robins, say in a forest, that's maybe not too big. Once that population gets pretty high, there's not as many worms to eat. Probably the population levels off. Say in thousands. And it is a function of time, t, as a function of t, say in years. We would like to have a differential equation whose solutions we already know what the graphs look like ahead of time, as far as their shape goes. Concave up and increasing at first, and then maybe concave down, but still increasing perhaps later on. We'd like that kind of differential equation that has those kind of graphs for solutions. However, there's still a benefit to writing the differential equation down instead of just making a graph like that, because maybe you can use the differential equation and the particular formula for the solution to make predictions. How good are the predictions? That's still uncertain. dp dt is going to be the rate of change of the population with respect to time. If the population is growing, this will be a rate of growth. It's possible, though, that if we are above the carrying capacity of the environment, that maybe the population declines. Maybe they're dying faster than they're being born. How do we reflect exponential growth when p is small? Maybe we should have an exponential growth kind of term here, a constant times p. If I left the differential equation just like this, dp dt equals k times p, that would be a case where the rate of change is proportional to the population. That's exponential growth. We've already seen that kind of thing. So what should I do to modify it to take into account limits on the environment? There's lots of things you could try. You might try maybe subtracting a constant here or something like that. Instead, what I'm going to do is I'm going to multiply by something. I'll put it in parentheses. That's close to 1 when p is close to 0, and close to 0 when p is close to some limiting carrying capacity of the environment. With a little bit of thought, it would reveal 1 minus p over some positive constant, I'll call it L, is the thing to use. L is the carrying capacity of the environment in thousands of robins. Maybe L is 10, for example, representing 10,000 robins. If you got 10,000 robins in this forest, the birth rate and the death rate are the same. For every robin that's born, a robin dies. Okay, of course, that doesn't mean a robin being born causes a robin to die. It's just that on average, over time, they equal out. This is something that is close to 1 when p is close to 0, right? Because if p is close to 0, then you've got something close to 1 minus 0, 1. And it's close to 0 when p is close to L. Approximately 0 when p is approximately L. Think about it. When p is close to L, this fraction is close to L over L, close to 1. And so the difference is close to 1 minus 1, 0. That's the simplest thing you can think of with those properties. You could come up with other expressions that might have similar properties, but they would be more complicated. Now, I could multiply this out. I think just for the sake of doing so, I will. I could write this as k times p minus k over L times p squared. I could multiply that out, but it's actually better to leave it in factored form, both for separating variables to solve the differential equation and for the sake of making the slope field. It's a bit better to leave it in factored form. I'll give this function a name. I'll call this f of p. It's my right-hand side function. It only involves the dependent variable p, not the independent variable t. So this differential equation is autonomous. It's independent of t on the right-hand side is what that really means. And if I make the slope field, what that's going to mean about the slope field is that the slope marks are going to have constant slopes along any horizontal line. Where p is constant, p is the vertical variable. Doesn't matter what t is. Let's go ahead and make the slope field right away here. I'll make the slope field before I solve the differential equation. T is a function, or TP axes. I'm not trying to graph this quadratic, though I could. And I think I will graph the quadratic over here to the right, a separate graph with axes labeled differently. P horizontal and dp dt equals f of p vertical. That'll be a graph of the quadratic that will help me understand the slope field. What I'm really after is the slope field and what solutions of the differential equation look like that follow the slope field. If I also happen to graph this quadratic as an ordinary function of p without bothering to think about the differential equation, maybe that's informative still. Let's just go ahead and think about slopes. Let's start to draw the slope field first. Think about this expression. For example, what values of p will make this 0? If I set this equal to 0 and solve for p, what do I get? I get p equals 0 or p equals L. The two values of p that make that 0. Sort of just focusing on the right-hand side here. With regard to the slope field for the differential equation, those are the horizontal lines where the slope marks are going to have 0 slope. P equals 0 and p equals L. In the slope field, you're going to have horizontal lines with a slope of 0 because those are points whose p coordinate, whose second coordinate makes the right-hand side 0. And again, it doesn't matter what t is because there's no t on the right-hand side. What about other values of p? Well, maybe I'll make this graph next to help me figure it out. Again, this right-hand side function, this f of p, is a quadratic. The coefficient of p squared is negative. The k and l are positive numbers, so because of the negative sign there, this is a negative coefficient. Graphs of parabolas, of quadratics are parabolas. Opening upward if the coefficient of the squared term is positive. Opening downward, concave down if it's negative. It is negative here, so we have to have a concave down graph. Where are its horizontal intercepts, look at this factored form, they are at P equals 0 and P equals L. But in this graph, P equals 0 and P equals L are on the horizontal axis, not the vertical axis here. These are different graphs, planes labeled in different ways. I'm just hoping this graph helps me understand the graph over here of the slope field. If you graph this quadratic, then it looks like this. It's upside down parabola. In fact, the peak is also at L over 2. That's where the right-hand side function has the highest output. Coming back to the slope field, when P is L over 2, P is the vertical axis now. That again is where the right-hand side function has a highest value, meaning the slopes in the slope field are steepest, highest. These are the steepest marks in the slope field with positive slope. If P is close to 0, not many robins, in this graph on the right, the output of the f of P function is positive but small. In the slope field, we get slope marks that have positive slopes, but close to 0. They're almost horizontal. On the flip side, if P gets close to L over in this graph, close to L, but just barely less than it, f of P is a small positive number again, meaning in the slope field, we get small positive slopes again. And since solutions in the slope field have to follow the slope field, anytime they pass through a midpoint of one of these line segments, it must be a tangent line. Solutions look about like this. And in fact, being an autonomous equation, all solutions are, well, take any solution and translate it horizontally, you've got another solution. Here are some other solutions. They are horizontal translations of the first one. They do have different initial conditions at time 0. What about other initial conditions like, well, like above this equilibrium solution up here, and there is an equilibrium solution right there that will end up being stable equilibrium solution. Above it, solutions must decrease because if P is bigger than L, the L, by the way, is right here. If P is above L, in this graph, that means the f of P function is negative output. And that means the slope field has negative slopes. Slightly negative if you're just barely a bit above L. Larger negative numbers, more negative if P is further above L. And yes, solutions up there decrease toward the carrying capacity. If you've got too many robins that are shipped in at time 0 and they're set free, there's just not enough food for all of them. They're going to die faster than they're born. Models like this are oversimplifications, right? In reality, whether you're talking robins or you're talking people, there are lots of things that go into what happens with the population. We're oversimplifying reality. And in particular, like with the equilibrium solution, we're pretending that the population stays exactly constant all the time, when in reality, it's going to go up and down at least a little bit. You can draw the slope field even when P is negative. When P is negative over here, the output of the f of P function is negative. And that means in the slope field, you get negative slopes. Slightly negative when you're just barely below 0, more and more negative as P gets more and more negative. And solutions decrease like this. But that's not important for the application. Mathematically, it still exists, and this is still, P equals 0 is still an equilibrium solution, but that one's unstable. Unstable equilibrium solution. When I teach differential equations with linear algebra, which some of you may take this fall, I really emphasize this f of p function. And I also emphasize that when the slope at an equilibrium point is positive, p equals 0 here corresponds to this equilibrium solution here, then the solution is going to be unstable. And when the slope of the f of p function at the other equilibrium point is negative, that's going to correspond to an equilibrium solution that's stable. And that observation generalizes to higher dimensions and matrices and things called eigenvalues. Eigenvalues, I love that word. Okay. These things all generalize. Another thing that we do in DiffyQ with linear algebra a lot is we take slope fields for autonomous equations and collapse them onto the p-axis, effectively ignoring t, except in your mind. What do I mean by that? We say, hey, solutions in here are going up, solutions up here are going down, solutions down here are going down. I could just draw that information on just a plain old p-axis like this, with L here, 0 here, upward pointing arrow there, downward pointing arrow here, downward pointing arrow there, indicating the direction that solutions go, increasing or decreasing as time goes by. And the equilibrium solutions become equilibrium points. The one that's stable we call, in this context, a sink. It's like water going down the sink. And the one that's unstable we call a source, water going away from a faucet. One-dimensional water along a line. But we can think that way if we want. That's called a phase line. I'll just write phase line. This generalizes to higher dimensions, even for us today and here, when we do very shortly the predator-prey model for robins eating worms when there's plenty of worms, and starving when there's not many worms. That's going to be our predator-prey model that we're going to shortly talk about. It's going to be a phase plane instead of a phase line, and time t will have to just be in your mind, in your imagination, not literally drawn. Like a parametric curve with motion. We drew parametric curves, like, say, the Lissajous figures going all over the place, right? T was in our minds, or we could animate it with Mathematica. But now let's go back to the differential equation and actually try to solve it. Yikes. Doesn't look so easy. We can separate variables. T and P are the variables. K and L are constants. Get all the P's on the left, all the T's on the right. There's only one T, a dt. I'll, quote unquote, pretend to multiply both sides by dt to cancel it over there, and divide both sides by, say, P times 1 minus P over L. I'll keep the K on the right. Let's show the details of that now. So the differential equation is, again, dp dt equals kp times 1 minus P over L. Separate variables, write it as dp over P times 1 minus P over L equals K dt. Integrate both sides. Right-hand side, as it always seems to be the case, is easy. KT plus C1. Left-hand side, oh, definitely harder this time. One thing I can do to make it a little simpler, to not have fractions within fractions, is I could multiply the top and the bottom of this by L, which is the same as multiplying by 1, so it doesn't change it. And in the bottom, distribute the L through the parentheses there to get rid of the fraction within the fraction. So I could write it as the integral of L over P times L minus P dp equals KT plus C1. But now what do we do? How do we do this integral? That's a rational function of P. Do you remember what technique we need to integrate rational functions? The A and the B, what's that called? Partial fractions. Partial fractions, our favorite technique. Not. Well, okay. It's not that bad. It's not that bad. At least in simpler cases, it's not that bad. You can come up with examples where it's really difficult. But our examples are not too bad. By the way, we use partial fractions in DiffEq as well when we do something called Laplace transforms. Partial fractions come back yet again from the dead. We'd like to break apart this fraction, break it up into partial fractions. Kind of a silly name, but we're stuck with it. We'd like to find A and B where this is true no matter what P is. Multiply both sides by that common denominator there. P times L minus P to get complete cancellation on the left, leaving you with an L. If I multiply the first fraction on the right by P times L minus P, in my head, the P's cancel. I'm left with A times L minus P. And if I multiply the second one by P times L minus P, the L minus P's cancel, leaving me with a B times P. Plug in special values like 0 and L. If P is 0, I get L is A times L plus B times 0, which is A times L, which means A is 1. And if I plug in P equals L, I'll get L is A times 0 plus BL, which is BL. So B is also 1. How about that? Nice and simple. You can always double check it by plugging those back up here and add the fractions by getting a common denominator. But now I can write that integral up there in a new way. Integral of 1 over P plus 1 over L minus P. Here's the original integral again. The integrand function was L over P times L minus P. Since A and B are 1, we can write that this way. That's got to be KT plus C1. What do we get when we integrate the left? We get logarithms. Ln of absolute value P, careful, minus Ln of L minus P in absolute value. Why do we need the minus sign? It's because the minus sign here is why. If you check this with the chain rule, you need the chain rule because the inside function is not P, it's L minus P. The derivative of the inside is -1. Cancels with this negative sign to give you a plus sign. If instead you checked it by integrating with, say, substitution, you'd let W be L minus P, dW would be negative dP. So you're going to get a negative sign, and that's essential to not get the wrong answer here so that we can get the right answer. Difference of two logs is the log of the quotient, and I can also combine the two absolute value signs into one absolute value sign. And now it's starting to feel familiar. Get rid of the logarithm by exponentiation. Looks like the absolute value of P over L minus P is e to the C1, e to the KT. I guess I'll call that C2 e to the KT. Get rid of the absolute value signs, pseudo-justified by calling C2 C3. And then don't forget what you're trying to do. We're trying to solve for P. Still seems kind of complicated. Well, effectively, you can cross multiply. Got effectively an equality between fractions. P times 1, P must equal the product of those two things. L minus P times C3 e to the KT. Hang with me here. Nice one. Solve for P, solve for P, solve for P. Okay, I better distribute this through the parentheses here. And then add the expression involving P to both sides. It looks like we get P equals LC3 e to the KT minus PC3 e to the KT. And that means if I add this to both sides, look where I'm pointing, and factor out a P after doing so, I'll get on the left P times 1 plus C3 e to the KT equals LC3 e to the KT. I did 2 steps there at once. I added PC3 e to the KT to both sides to cancel it on the right. And then after doing so and having it on the left, I factor it out of P. Almost done. P equals LC3 e to the KT over 1 plus C3 e to the KT. And instead of calling it C3, we could just call it C. And you could call this a general solution. However, it's not the way a general solution in this example is most typically written. What people usually do here, though you don't have to do this, is they usually try to just get one E in there and make the top a constant. What do? They divide both the top and the bottom by C3 e to the KT. Which is okay to do as long as C3 is not 0. And on the bottom, you've got to use the distributive property as well. So what do we get? P is going to be on the top, everything but the L cancels. That's part of the reason why this last step is done. In the bottom, with the product here and here, those are complete cancellation to 1. So write another 1, but that's actually kind of a different one than this one because it comes from something different. I mean, yes, they're both 1, but I got this one, not from that one, but from this 2. The product of those 2 things. And then with the product of these 2 things, yes, I could write it as 1 over C3 e to the KT, but it's more common to write it as just a plain old C e to the negative KT. So the benefit of this is you have a constant up top. I guess that's kind of nice. And you only have e to a power appearing in just one spot. Effectively, the C is 1 over C3. However, there's still kind of a defect with this. This is a general solution. It's not the most ideal general solution, though it's probably the way most people write it. Because what's the most ideal situation for a general solution? There should be 2 things that it happens. First thing is it should be a solution no matter what C is. This will satisfy that for sure. We'll check it here in a minute. Secondly, any solution should be able to be written this way. It does not quite satisfy that. There's one solution in particular that's not in this form for any value of C. Though it is in this form if C3 is 0. It's the 0 function. Satisfies this form when C3 is 0, but there's no value of C that will make this thing always 0. Effectively, because we obtain C by dividing by C3. But before we solve a generic initial value problem, let's check that this solves the differential equation, no matter what C is. This is a complicated kind of checking, the most complicated example that we've had. But it's doable, and theoretically, you should be able to do this on the test. Maybe without so many letters, maybe particular numbers instead. What does the left-hand side of the differential equation simplify to? The left-hand side of the differential equation was dp dt. Upon substituting the function, this is what it means to check. Substitute the function. In this case, it means to take the derivative. It's a quotient. I need the quotient. Well, I mean, I could write it as L times this thing to the -1 power, but let's just use the quotient. Low d high, the derivative of L is 0. That's low d high minus high d low. If I take the derivative of the bottom, the derivative of 1 is 0. I get, from the chain rule, the derivative of that is negative kc e to the negative kt. An extra factor of negative k comes into play because of the chain rule. Low d high minus high d low over the square of what's below. Now let's simplify. The 0 makes the first term up top go away. With the second term, the two minus signs cancel, giving me LKC e to the negative KT. And then that gets divided by 1 plus C e to the negative KT quantity squared. The right-hand side of the differential equation, you've probably forgotten by now, but it was K times P times 1 minus, that's a 1 there, 1 minus P over L. Substitute the proposed solution into that as well in place of P. Substitute this formula in red in place of P. I get a K, and then I get this P, which is L over 1 plus C e to the negative KT. Then in parentheses times 1 minus P over L. What's P over L going to be? Take this P and divide by L. That's going to make the L up top cancel to a 1. 1 over 1 plus C e to the negative KT. That's K times P times 1 minus P over L. Simplify. This K can go into the numerator there and get K times L. And inside the parentheses, I can get a common denominator of 1 plus C e to the negative KT. 1 becomes 1 plus C e to the negative KT over 1 plus C e to the negative KT. But then we're also subtracting 1 from the second fraction. The 1s cancel. And after multiplication of the numerator and denominators, we get the same thing we got with the left-hand side. And we are very, very happy that these two things match. Very, very happy. Might seem like it's complete luck. It's not complete luck. Might seem, would this happen for any function? They would get the same thing. No, definitely not. Pick a random function, it won't work. You can try it. It does work with any function of this form, no matter what C is. The C is irrelevant. It still works. The L and the K do need to match the L and the K from the differential equation. The L and the K there need to match the L and the K there. Those do need to match. All right. Let's now solve a generic initial value problem, which is my favorite kind of initial value problem to solve, by the way. Generic meaning I've got an arbitrary P naught, say, for the initial population, not some number like 7. I really emphasize that a lot in DiffyQ with linear. It's got some importance beyond what you can even imagine. Let's say P naught is P of 0 is what's P of 0 going to be? Look at this formula, plug in T equals 0. L over 1 plus C e to the negative K times T, where T is 0. That's e to the 0, which is 1. So this becomes L over 1 plus C. When solving initial value problems, you want to solve for C. So that's what I want to do now. I want to solve this equation for C. Once again, cross multiplication is fine. We can think of this as being P naught over 1 if we like. So we get L times 1, which is L, equals P naught times 1 plus C. I can distribute the P naught through the parentheses, but I don't have to. I can just divide both sides by P naught right away. And then I can subtract 1 and say C is L over P naught minus 1. I also can get a common denominator of P naught and write this as L minus P naught over P naught, which is fine as long as I'm not dividing by 0. And that's another reason why the solution with initial value of 0 is missed. But then if I plug that back in for C, something almost magical happens if I simplify it. And the P naught equals 0 case does end up being included, which really ends up harkening back to the other form of the solution. Where'd it go? Oh yeah, right there is with the C3 in it, kind of being the better form anyway. So why'd we do that? It's just traditional. If I write the formula for the solution, and I'm going to use the phi notation and emphasize the initial condition as a subscript, L over 1 plus C e to the negative KT, where C is this, L minus P naught all over P naught. And then, yeah, if I multiply the top and the bottom of this fraction by P naught, which is fine to do because it is multiplying by 1, and distribute it through the bottom, so I got a sum on the bottom, this times this and this times this, then all of a sudden the formula does work even when P naught is 0. And here's the way it looks. This is my favorite form of the solution. Okay? You should be able to handle working with this if you have particular numbers. For example, if the carrying capacity of the environment is assumed to be 10,000 robins, represented by the number of 10 because the units of the robins is thousands of robins, and P naught is 500 robins, which would be 0.5 thousand robins, and K is, just to pick something specific, how about 0.08? We could ask and try to answer the question, when does the population reach 5,000? Equals 5. How long does that take? I didn't know what the answer was going to be in the first section. I ended up solving it. It's kind of a large value of t, which is probably not realistic if time is in years. But bear with me. I'm just going to plug these numbers in. P equals phi sub 0.5 of t. It's the 0.5 because that's what P naught is. L is 10, P naught 0.5. Plug all these numbers in and simplify. You get 5 over 0.5 plus 9.5 e to the negative 0.08 t. You actually could write this without decimals as well. You could replace 0.5 with 1/2 and 9.5 with 19 halves, and then multiply the top and the bottom by 2 to get rid of those fractions. I won't bother. I want to set this equal to 5 and solve for t. Now, it just happens to be the case, based on L and P naught, and what I picked there, that the numerators here are the same, 5. Didn't have to happen. But because they're the same, they both cancel to 1 effectively. And that ends up meaning this denominator here has to equal 1. I mean, I didn't have to do that cancellation to see that, but this denominator equals 1. Subtracting 0.5 from both sides means 9.5 e to the negative 0.08 t equals 0.5. Divide both sides by 9.5. And you get this, which is, if you write it as an ordinary kind of fraction, 1/19. Take the log of both sides, then divide both sides by negative 0.08. T can be written as ln of 1/19 divided by negative 0.08, which by properties of the logarithms is the same as ln of 19, divided by positive 0.08. If you're ever unsure of that, is that really right? You can always double check it. ln of 1/19 is this. Divide by negative 0.08, you get a positive 36.8. If you do ln of 19 divided by 0.08, you get the exact same answer. If you're ever unsure about that kind of thing that I did there. So about 36.8 years seems too long to wait for the robin population to grow from 500 to 5,000. What would make it grow faster? One thing would be a larger value of K. K does kind of represent the growth rate as a percentage, 8% in this case, when the population is small. If K were bigger, I'd be dividing by a bigger number there, and I get a smaller number there. It would grow faster when K is bigger. Okay, so you should be able to handle problems like this too. Can I clarify anything? Doing the arbitrary case is very powerful. It allows us to solve infinitely many problems at once. And then we can use this for any values of L, P naught, and K that we want. And maybe actually, this might be the case with, for example, trying to think about the population of the world in people, or billions of people. Maybe your goal is to really figure out what L is. You know, P naught is just whatever the population is right now, say. Maybe you know K based on birth rates, maybe, or maybe based on what the population is a year later, and you've got to figure it out. What's the carrying capacity of the Earth? Is it a valid kind of calculation? Is it a good model? It's not perfect, that's for sure. So you could argue whether it's really a good model or not. It ignores lots of complicating factors.